Thank you, Dave, for the introduction, and thank you, Chunyi and SJ, who can't be here. SJ, I hope you're online, still awake, for the invitation. It is amazing to see everyone in person, and again, so wonderful that we could all be here together. And also, I should add my thanks to the entire organizing committee, because as Dave was mentioning, the work to put together not only the original event, but to transition to this hybrid event is just astounding. So thanks to you all. What I'd like to talk about today is wireless networking, sensing and security, and focus on frequencies above 100 gigahertz. And so to start, if you all are probably too young to remember, and so am I, but the old wireless dream was really to take us away from these phone booths and just to have mobile voice. And mobile voice at the time was just extremely exciting and all we really wanted in wireless networks. But as we move forward, the question is, well, what are we looking forward to in the next generation of wireless? What are some of the things that we can't do today that we wish we could do? And so there are new performance milestones, terabit per second wireless LANs, latency milestones, robust, secure, and so on. And also fusing communications and sensing into the same devices and the same infrastructure. And so just to give a couple examples, some newly enabled applications, shown there is a virtual reality conference, and you can guess it's pre-COVID by how close they're all sitting and nobody's masked. But if you'll notice, all their goggles have a wire that we simply couldn't even possibly begin to do the density of bits per second per square meter. So that density spatially as well, and the latency that would be required as well. Likewise, new applications emerging, UAV networks, and they can have high resolution sensing, video, and communicate amongst each other. So I'd like to talk about spectrum, and there's a phrase, beachfront spectrum, and where exactly is that spectrum? And so I'd like to take you a little walk through different spectrum and what we're really looking for and why above 100 gigahertz, and what are some of the challenges and opportunities? Why would we even want it? And so if we start looking at spectrum and we ask about propagation, then we know from the Friese equation that the receive power is related to the transmit power by a 1 over distance squared term. And so we've got a bunch of constants in there in the 1 over distance squared term. And so if you start to ask, well, what is that really going to mean for us in the, say, practical wireless LAN scenario, 10 meters or so? And so if we had TV bands down at 500 megahertz, we lose 46 dB over that range. And so if we move up to Wi-Fi, then we've gone an order of magnitude, but then we've got the squared. So then we lost 20 dB. And now we're at 60 dB loss. And then likewise, if you move up to 60 gigahertz, we lose another 20 dB, and keep moving up to 300 and we lose another 20. So these 20 might not seem significant, but you keep adding 20 each time we go in order of magnitude. And we've actually got quite a big loss, losing 100 dB, more than 100 dB over only 10 meters. So it seems we should just stick with sub 6 gigahertz. That it's hard to imagine that we want to overcome those sorts of path losses. Yet now, what about data rate? So if we ask Shannon about what spectrum we should have, he'll tell us about this W term out front, that the capacity of the channel is proportional to the bandwidth of the channel. And so what kinds of bandwidths can we get? Well, again, if we start with TV bands, a typical digital TV band is at 5 megahertz. And then as we go to Wi-Fi, sub 6 gigahertz, the 20 megahertz channel that we're all using now, but also we can bond those up to 160. So we're gaining more than an order of magnitude there. Likewise, at 60 gigahertz a millimeter wave, we're gaining another order of magnitude, bonding up to 8 gigahertz. So can we, as we get to the new frontier above 100 gigahertz, consider channels that are even 100 gigahertz scale wide, and then go multiple orders of magnitude in terms of that available bandwidth? And lastly, sensing resolution. So with sensing resolution, we're ultimately constrained by the wavelength. It depends on what exact sensing technology we're using, but there's always a wavelength term in there, which is inversely proportional to the frequency. And so TV bands were at meter scale, Wi-Fi centimeter scale, millimeter wave at 802.11 is 5 millimeters and so on. And then we get down to millimeter. So for sensing, we would love to have these higher frequencies as well if we desire those sorts of resolutions. So can we have it all? So if we could be above 100 gigahertz and have the wide bandwidths that we would like, and also the high resolution sensing, then the question is, there was this GTGR term in there, which are directivity gains. And if we could use those terms to overcome the path loss, then could we potentially have all the things that we want, the high data rate, the high sensing resolution, and then what's the catch? What are the challenges? So I'd like to talk about the road ahead. So if we say our road ahead is we'd like to get terabit per second mobile and high resolution sensing, and I'd like to talk about two cautionary notes in the talk. And so one is the control plane to set all of this up, and so that's the control plane side, and then the other in the caution, the picture of the gremlin is security threats. So what are there new security threats that we should be thinking of as we go to higher and higher frequencies? So let me start with where we are today and with standards. And so the Wi-Fi standard 802.11ay, many of you are probably familiar with it. This is a tutorial paper we wrote with some of the authors of the standard at Intel. And it tells how we can do beamforming at 60 gigahertz. And I'll just briefly give you a couple slides to show how it's done today and show some of the challenges that we have. So for those of you who don't know about 60 gigahertz, the way it works, let's see, the fonts on my screen aren't showing those. I don't know if you can see them. Yeah, it looks a little crazy there, but you can figure out what it is. So we'd have an antenna array shown there on the right, and then we'd have beam steering with analog phases, those shown right to the left of those antennas. And those are typically discrete. That's really important, that they don't think of those as just an arbitrary phase delay. They're discretized, sometimes only 4 values between 0 and 2 pi. And those define beams that are referred to as sectors. So again, I'll show you a picture in a moment, but please don't think of a sector as just a nice little slice, a 3-degree slice. I'm going to illustrate it that way, and everyone does that. But we need to keep in mind that that's not the way the real transmission looks like for several reasons. And then the standard has mechanisms to adapt and select the sectors. I'll show you that. And also multiple streams. So if it's just an antenna array, it's not MIMO, it's just a phased array. But if we have multiple RF chains, then we've got MIMO capability too in the latest 802.11ay. All right, so how does it work? So the term used in the standards is a sector level sweep. So what this means is both ends of the link test communication on all their sectors. So they sweep around the sectors. And so showing there, the AP is sweeping, testing all of the sectors. Each sector has to be somehow labeled for the receiver. The receiver has to know which sector is this. Is this sector 1, 7, 10, whatever? Because the receiver might not even hear all of them. It might just hear a subset. And so, so the receiver is trying its best to listen in all directions. It's called quasi-omni antenna pattern. And so the receiver's listening in all directions best it can. Here, some of the sector says sector 17, whatever is the best, and feeds that back. And then the process repeats in both directions. The mobile does its own sweep. Sometimes mobiles have smaller arrays, so there might not be as many sectors. And then the AP will be in omnidirectional receive mode and determine the best receive sector. And that works. It's extremely successful. It finds the best pair of sectors. It finds the highest gain pair, the GTs, the GRs. It maximizes those. That's what the procedure does, and it successfully does it. Now, but then what's the catch? Well, the catch is if there's some movement. So just here showing a rotation and a translation. So if the receiver rotates, the receiver now needs to re-steer. The transmitter's still okay in this one case, but translation, actually, they both need to re-steer. So what's the big deal about re-steering? Also here showing a blockage, right? So if someone walks between the beam, then some of these beams are not able to, at these frequencies, penetrate large objects and humans, and so then we would have to re-steer them across over a reflected path. So what's the big deal? So we retrain, we do a sector level sweep. Surely that can happen extremely fast, and there's no problem here. Well, the problem is that while that sector sweep is happening, data can't be transmitted. The spectrum is being used for something else, and so that's a delay, it's an outage, and the transmitter and receiver have to pause communication. All transmitters and receivers, the entire network pauses while that occurs. Now the question is, what's the time scale for all this? And I'm showing an example of the time scale of data. Data is shown there in green, and the sector sweep is shown there taking longer than data. So our outages are layer 2 frame scale outages in order to do this. It's a significant time. And the reason is all those sectors have to have some labels on them. They've got to be telling each side what they're doing, and so that they can align the beams. So if we have to do this frequently, then the overhead keeps growing more and more. And so in some of the early 60 gigahertz devices, a typical beam pattern is the one shown on the left. And you might say, why is that thing so messy and looking like a blob? And there's two main reasons behind it. One is that the discretization of the weights. So you don't get to arbitrarily choose the beam steering weights between every antenna, but they're discretized, and that gives irregular shaped beams. And the other is the limit of the number of antennas. I think this might have been 16 or 24 in that range. As we go higher, then we can get even more directive beams above 100 gigahertz, several hundred. This is an experimental, I think, at 300 gigahertz. And we can get extremely directive looking patterns. And so if we have a pattern such as that shown on the right, then the search space has grown even more. The sector sweep time can even grow. So can we rapidly re-steer the beams? And so I'd like to talk about some of the devices that have promise for beam steering above 100 gigahertz, and one is a leaky wave antenna. So how does a leaky wave antenna work? So it's a really interesting device because it starts conceptually. I'll show you a practical one in a moment, but it starts with two parallel plate waveguides. And if you inject an electromagnetic wave into there shown with the green ray, then it's guided through the waveguide. There's boundary conditions that the electric field is 0 on both the metal plates. But then if you put a slot on the side, then the wave's behavior inside the guide, which you can view as reflecting off of the different, off of both the sides, then emits from the side. And the vast majority of the energy emits from the side. So the beam is actually coming out of the side when you have that slot in the waveguide. And so the beam is coming out of that slot, and the interesting thing about the leaky waveguide, the valuable property, is that the angle that it emits is related to the frequency of the input wave. So once you define the F frequency in the denominator, C over 2 BF, where B is the width of the plates, then the angle that it emits is related to that by the equation I have there, inverse sine C over 2 BF. So what that means is it gives us a way to steer the beam because we can choose the input frequency and steer the phi based on that. Now, I said it was new, and I put new in quotes because I did want to say this is a 1940 device, and here's the patent on it, and the pitch in the patent is exactly the one I gave you just a moment ago, that the frequency is coupled to the angle, and that's a valuable property that was used even in 1940. But why are we so excited about it now? Well, beam steering above 100 gigahertz can be a challenge, so some of the early work with leaky wave antenna used the leaky wave antenna as a way to steer beams. And so the idea was, well, if we can tune the frequency, then we can use this relationship to steer the beam. And so here, if you view that parallel to the plates is higher frequencies, and then as you get more to broadside, those are lower frequencies, then we can adapt the frequency in order to steer the beam, or simply send information on different frequencies depending on where the particular user is. So this is the highest frequency beam steering mechanism to date. It's been demonstrated up to terahertz scale. I'll actually show you some data up to about 800 gigahertz. It uses a single antenna, so there's no phased array, there's no MIMO. It's a very simple device. So we have a way to steer, we have a way to rapidly steer, but we're still left with that question about where do we steer? So now I can instantly steer any direction at terahertz scale, but I still need to know, well, which direction are each of these receivers coming from? So the key idea that, that I want to tell you about that you may have heard about even in a previous MobiCom, this was one of my PhD students' work and from my group. And the idea is, we call it a THz Rainbow. And so the idea is if you put in a pulse that's broadband, and so showing that with white light. So view the pulse going in there as containing all frequencies. So if we shine white light in there, and then it contains all frequencies, then what emits when we have angle frequency coupling? Well, each frequency emits at a different angle. And so in essence, you have a rainbow coming out the other side. So what does that mean for localization? Well, that means that shown here in yellow, the receiver is around the yellow part of that rainbow. So that means if I shine a rainbow here and you all want to know, well, where are you? Well, you know, red's over here, violet's over there, and now you all know exactly where you are all relative to me instantly, because the pulse was nanosecond scale. So within a nanosecond, everyone knows where they are related to me. So we called it one-shot location discovery, and it's a nanosecond, all receivers, so everyone in this room could tell where they are relative to me within a nanosecond. The key thing is the things that it doesn't have. It doesn't have trial and error testing of different directions. It doesn't have phase information. There was no, all the things that took time before. There's no explicit labeling of sectors. There was no need for a receiver to do equalization first. And all those complexities, no signal processing, no array processing. It's the simplicity and the near instantaneous nature that makes this promising. Okay, so how does this work in a real system? So the equations I've shown you so far are predicted by Maxwell's equations. You can also use this, develop more of a model, not just to say what's the peak emission angle, but what's the distribution of the emission angle. And so this is shown here, a heat map. And so I'm showing angle on the x-axis and then frequency on the y-axis. And so you can see if you want to steer towards 30 degrees at angle, then that gives you about a 300 gigahertz center. And then you've got a spectrum that's usable in this particular setup of maybe 100-ish gigahertz around that. So you can use extremely wide bands and then tune the angle by tuning that center frequency. We measured some of these in the lab. And so the left is a theoretical one that I just showed, and the right one is a measurement in the lab. And so what you can see is that we've got additional modes. So I was showing in the model just the first transverse electric mode, and then there's higher modes shown there with the multiple these other additional arcs there, TE2, 3, and 4. And then also you see some imperfections of the leaky wave antenna creating irregularities. But the point is that for each frequency, we can steer the beam in practice in a real leaky wave antenna, a simple device that we manufactured at a normal machine shop, and steer the beam and also know the signature for each receiver. So we did some experiments with it, and just to give you a sense of relatively where the errors are, it's less than 5 degrees in over 80% of the cases. So shown here, you can see the ideal that we'd have is to be right on the red line, and then in the center, in these degrees 20 to 60, we're close to being on the line, and then we fall off as we get to the higher angles. And so you might remember that the higher angles here, we're getting very flat here. So that becomes much harder to resolve what the exact angle is there. So the point is that is again, there's been so many localization papers and beam alignment papers. I think it's not as much about having the bake-off of who can get the absolute best number here, but what are the requirements to get that functionality, and what is the time taken? So the single shot, the spectrum only, and no phase information. Okay, so I'd like to turn to sensing, not for the purposes of communication. So I'd like to turn to radar and the question of, if we have an access point and we're not trying to align beams, I'm just simply trying to understand the physical environment around me. And so now the AP is sending signals, bouncing them off different objects, and then measuring what comes reflected. And I'd like to show you a result. I promised millimeter scale sensing, and so I wanted to show you a millimeter scale resolution sensing. And again, there are many MobiCom papers at decimeter level and so on, and that's primarily, well, they're always using phased arrays or MIMO, and they are also typically using much lower frequencies. But as we get up to these higher frequencies, there's new capability for millimeter scale. And so I just want to show you a result. This is not my own result. It's Middleman Lab at Brown University, one of my collaborators. And he used the same THz Rainbow idea. And so the idea is you shoot out a rainbow, and then I see what colors are reflecting back to me. And so if red reflects back, red as my metaphor for, say, 100-ish gigahertz, and if red reflects back, then I know it's very close to broadside. But then on the other hand, if I'm getting higher frequencies, say 900 gigahertz, then I know it's much closer to parallel. So as I get those reflections back at different frequencies, then I can tell where the device is reflecting from. And so in his experiment, he took a metal rod that was only 10 millimeters in radius, and he moved it along a triangle. So that's the ground truth triangle in blue as he's moving this rod around. And then the red are his measurements of where is the rod. And this is purely from the colors again. There's no array processing. It's again, all the things it doesn't have that are really amazing about there is no array. It's simply a parallel plates waveguides. That is what is behind all this. And so he got accuracy down to 1 millimeter and 1.2 degrees. This is the raw data, but that's the 1 millimeter and 1.2 degrees is the average. And then real-time computation. There's still some FFTs to do to process the spectrum and do a best match and so on. So there was some computation to do, but it was in the 200 millisecond scale. For my more cynical friends who are thinking there'll never be parallel plates on a iPhone, I agree. We won't be seeing those sticking out anytime soon, but there are circuit realizations of the same idea. And I want to show you one coming out of the Sengupta lab at Princeton, and it's he realized the idea of the THz Rainbow. He called it the THz Prism in CMOS. And so also he's using a narrower frequency. We use 100 all the way to 900 gigahertz, and he used 360 to 400 gigahertz. And because you can tune how wide it is, and it just depends on the parameters that you choose in order to do the localization. We had a very wideband system, so we used all the bandwidth. For CMOS, it was more convenient for him to use a much more, still 40 gigahertz of bandwidth, but narrower compared to what we did, very wide compared to today's system. So he used 40 gigahertz of bandwidth and built a CMOS implementation, the same idea, and he demonstrated even better accuracy than we could get with the parallel plate. So he was down to a couple degrees of accuracy there. So devices coming out that can take the physics from all the way from parallel plates and Maxwell's equations to real CMOS implementations and get these integrated onto devices. Okay, so the takeaway message about communication and sensing is that today's way of doing things is shown on the left, and that new ways that we can think of are shown on the right. So today we think of phased arrays array processing, each beam having a unique ID so we can label it. This is beam 7, you receive beam 7, so therefore you feed that back to me. The trial and error testing each at a time, and then microseconds by the time it's all over. And microseconds maybe not seeming too long, but if we're trying to go at a terabit per second, it's a long outage. And then of course array processing, which can be extremely difficult to do at these data rates. So a future way to do it, new devices, the devices have new physics behind them, angular dispersion. This is something that exists in all systems, wireless systems, but it's just relatively trivial effect at sub 6 gigahertz. It might mean that if you use the upper end of the 6 gigahertz spectrum versus the lower end, the beams might shift by a fraction of a degree or two. So nothing that you would be able to exploit in any meaningful way. Yet as we go above 100 gigahertz, it starts to be a dominant effect. Angular dispersion is a key effect that we're seeing in systems, and we can exploit that in order to beam steer and also in order to localize. So we can now do this with a single antenna. Parallel plates, I think, are just so nice to analyze and use in the lab. But for practical systems, CMOS leaky wave antennas are the way to go. And then each angle has a spectral signature. And then we get to do all angles at once by putting in a high frequency pulse. And that gives us, that's the foundation for nanosecond scale alignment of beams, but also for radar as well. So the radar can send out pulses and then be getting back and doing the processing in real time. Okay, so for the remainder of the talk, I'd like to shift gears a little bit to security. So I talked so far about sensing and communication. And so if we have leaky wave antennas, we have terahertz scale frequencies, and we have high directivity, then what are the new security opportunities or threats, or what does the landscape look like above 100 gigahertz? And so there's a lot of optimism out there in terms of the beam width. So I showed you a picture of a very narrow beam. And so if you start to view, say, a several degree beam, then there's optimism that that beam is inherently immune to eavesdropping. So if I'm beamforming on this side, then doesn't it seem pretty impossible that someone over on the other side of the room can begin to intercept it, even if they've got a great high gain antenna? But so that would be a relatively robust against an eavesdropping attack. So these are some quotes from the popular press and some from papers saying, well, 60 gigahertz and above will have covert communication, will have confidentiality, provide security, and so on. So why the optimism? Well, let's look at a couple scenarios. So one scenario is the wireless LAN. And so we've got the access point, and we'll call the access point Alice. And we've got Bob on the laptop, and we have a highly directional Alice to Bob link. And likewise, we could have backhaul or point-to-point rooftop links above a terahertz. These could be kilometer scale. There have been multiple links demonstrated at these distances above kilometers and above 100 gigahertz and approaching terabit per second at rates of several hundred gigabits per second. And so if we've got such a point-to-point link, we might also think, well, who's possibly going to intercept that communication? And so what I'd like to convince you of a threat that should keep you up at night, and we'll call it the MetaSurface in the middle attack. And so the MetaSurface in the middle is a device that's a strong adversary, and a MetaSurface can be used to manipulate electromagnetic waves. And so the surface, in principle, can do any sort of transformation it wants. I'll convince you that in a few moments, that whatever electromagnetic wave is impinging on it, then there's a possibility to change the output with atomic level control. So the scenario I want to talk to you about today is a MetaSurface in the middle attack, where the MetaSurface here shown in red has two objectives. One, let the Alice and Bob link go. not disturb it. So Alice and Bob think everything is wonderful. There couldn't possibly be an attacker trying to intercept the signal. Yet, the MetaSurface is going to diffract a portion of the signal away towards herself. So shown in the wireless LAN scenario in the left, the eavesdropper is sitting there outside the room, and maybe there's some tabletop object or some numbers when you go to cafes or posters or whatever, and that contains an embedded MetaSurface. Or in the rooftop link, we've got a drone flying in, or potentially something else on the rooftop structure in order to diffract part of the signal. So there, Eve is shown on the ground. This can be done for the presentation. I'll just do a 2D re-steering of it, but of course it can be a 3D as well. So we'll call this the MetaSurface and the metal attack. So here are the research questions. So first, how can Eve design such a MetaSurface? She's got to use a transmissive substrate so that the signal goes through. She's going to take some meta atoms as a building block, and she's going to arrange these atoms on a surface and try to do the diffraction that she wants. She also has to build this device to operate above 100 gigahertz, because Alice and Bob are using a terabit per second scale links above 100 gigahertz, so it has to work at those frequencies. And of course, can we actually experimentally show it? This is an experimental conference. We're an experimental group. So you wouldn't believe it if I just showed you a simulation. So understood, we're going to show you a experimental demonstration. And my student, Jean-Paul, just this paper coming up in YSEC, and there he is right there if you have some tough questions for him. Okay, so how can Eve do this? So how does the MetaSurface in the middle work? So Eve, so I'm showing in the bottom, there's a picture. We've got Alice and Bob, and we'll envision the MetaSurface at broadside to Alice and Bob. And then Eve positions herself theta degrees away. So Eve knows what theta is. She knows where Alice and Bob are, and she moves theta a safe location away. And what she's going to do is create an anomalous diffraction using generalized Snell's law. And so just to remind you of what Snell's law is, it's everything not highlighted in yellow in the equation. So there you might remember from your high school physics that you've got this angle theta, and it's related to the inverse sine of, and then you've got the fractions that the refraction indices n of the two sides. And then you've got the angle of incidence gamma there. And so Snell's law itself looks completely unhelpful to Eve, right? Because the n's for air are 1, and then it's broadside, so sine gamma 0. So Eve is not really looking too good unless she can put Bob underwater or something like that. So how can Eve possibly get a diffraction going? So generalized Snell's law is what's going to help her out. And the basic idea is this additional term shown here highlighted. And the idea is that if she can design this surface here to manipulate the spatial profile of the wave, so she's going to have to shift the phase of the incoming wave differently across the MetaSurface. So X is across the MetaSurface. At each point on the MetaSurface, she has to shift the phase differently. And we'll call that phase, she's going to shift the wave phi of X. How does she have to shift it? Well, actually, all she has to do is create a d phi dx here, which she'll make a constant. So she's got to make it a constant change over the X. And then with this constant, then she can create the theta that she wants, because all these others are constants. C is the speed of light, FC is the carrier frequency. So that's Eve's goal. So Eve's just going to use generalized Snell's law and create an anomalous diffraction, and we'll see if Eve is successful in this way. Okay. So how's she going to do it? She's going to do it atom by atom, create the surface. Let me start with a material analogy. So if this was not a metamaterial, if it was a physical material, then one, she could be using the two refractive indices n in order to create an n on the left side and an n on the right side, or maybe, for example, for a lens, and you'd have plastic or glass for the lens, and then you'd use the structure of the shape structure. So a lens, you'd give it that concave structure, and that would create different delays through the different n, and that would give you the phase profile you want. So here, we don't have a physical structure, it's something flat. and our ends are 1, we're stuck. So how does the meta atom look like? So we'll start Eve with a very simple meta atom called the split ring resonator, shown up here in the upper right. And so this is a piece of metal, and we're in the end going to have the metal on a paper substrate. So you can view this metal as just sitting there on paper. And here's the metal, and then there are a few parameters that Eve has. So Eve has the radius, the opening angle, alpha, and also the orientation angle. She can rotate it. And so with this meta atom, she can create a different phase depending on how she chooses those 3 parameters. So in particular, Eve views that she's got a menu of alphas and betas and Rs that control 5x the phase profile. So I'm showing it here in the heat map. So there's a heat map. So let's suppose that Eve says, okay, I know what I want to do. I want to diffract that signal towards me. So I need a particular phase delay at this particular point on my MetaSurface. Let's just say she wants a 50-degree shift. Then where does she go? Well, she looks on the menu here and say, all right, I want a 50-degree shift. 50 looks like some pretty dark blue. So I'm going to choose this point over here. And what does that mean? I've got a radius of my meta atom there, and I've got a split angle, that opening angle, maybe a 120 degrees. So it just told her how to design the atom. Wonderful. So she's going to use that. And she's going to do atom by atom selection, and Eve here has a full 2 pi phase control. So she's, just by playing with this atom, she can adjust the phase however she wants. All right, how does it work? So I said in using the generalized Snell's law, she needs d phi dx to be a constant, so she's got to change it over space. And we'll call that constant 2 pi over gamma. We'll make gamma the constant that Eve will control. So she's going to choose a desired theta. Let's make theta will be 22 degrees in the experiment, so we'll make it 22 degrees. And Eve's got to get a phase profile. So over x here, so I'm showing x on the horizontal axis. So this is x where she had to change her selection of atoms so that each one gave a different phase profile. So here's the first atom that she chose off the menu. And then to select that atom, she got a phase shift of almost 3 pi over 2, shown there in the red. And she just can't choose that atom for the entire surface. If she chooses the same atom for the entire surface, the wave just goes through, and there's a constant phase profile, and nothing happens. It doesn't work. But if she chooses the atom next to it, right there, notice it's a little bit bigger. The opening's a little smaller. She chose a different atom off the menu of atoms, and then she now got a phase profile down here a little bit lower, close to where are we on there? Pi or so. So she's getting this, it's a constant slope. That was her goal, to get the red line to be a constant slope. She did it by laying out these 8 atoms here over space. So she's got a spatial period, gamma equal 8 meta atoms, and then she repeats it. So this is just, each of these will be columns, and she'll just copy paste the columns over and over. The amplitude, she would love it to be flat. She couldn't get it exactly flat. Because she doesn't have perfect control over both of those independently, but we'll see. Is that going to hurt her goal by not having a perfectly flat phase profile? For Eve, the blue not being flat is just simply error, but she's very happy that she got a straight line for the red covering the full 2 pi over gamma, and gamma chosen to get her the angle she wants. Okay, so let's implement this. So the traditional methods are photolithography, and photolithography is wonderful for its high resolution, nanometer scale resolution, but it's also a high cost and slow method to do. So the method that we use is a rapid prototyping method called hot stamping, and it's rapid and it's inexpensive, and it can be done in less than a minute to create one. Inexpensive because it uses common materials that you can find in a craft store. So inexpensive, we brought a few with us. I think there's one next to you, Victor. I promise you I'm not eavesdropping, but there's, I think, one on the table there. Yeah, there you go. That's the MetaSurface in the middle. And it's a hot stamping method on a paper substrate. And so how does it work? Well, we print it on a paper substrate to get a transmissive surface. It doesn't have to be paper. It can be anything that's transmitted. It can't be a metal reflector array, but we can have plastics or other materials that are transparent at above 100 gigahertz. And then Eve takes this pattern. I just showed you one row. So she repeats the pattern vertically across the MetaSurface, and then takes that and then copies and pastes that. So she's copying this one row horizontally and vertically, and it's just printed on a normal laser printer. And then once it's printed, now we've got the toner on the paper, and then feed a metal foil, which is again used for typical crafts for people that like to do hot stamping. And that's fed through a laminator. And then the heat and the pressure of the laminator bond the metal. So this is a way that any pattern at this scale, these are sub-millimeter scales. If you remember from the prior slide, gamma here is 6 millimeters, so our atoms are less than a millimeter. So you can view the width of that one block that I'm showing there as 6 millimeters, and that just repeats over and over. So that's Eve's surface, and there are many other ways she could make a surface, but this is the rapid prototyping way. Okay, now does it work? So here's the experimental scenario. It's a tabletop setup where we send a wideband pulse from Alice to Bob, and Eve is going to be located 22 degrees angularly away. We're using a scaled lower power, so our distances are close. This is less than a microwatt of transmit power. So obviously we're not getting kilometer scale links with that sort of transmit power. So we've got everything scaled down for a tabletop analysis. And so the wideband pulse goes in at Alice, and then Bob and Eve measure the received signal. Bob's broadside to the MetaSurface in the middle. There are lots of experiments where it's not perfect and things are not perfectly aligned and so on, but I'll just show you the case where the receiver, Eve, here is 22 degrees, where she designed the spec for. Okay, so let's start off. So there's Alice on the left, Bob on the right, Eve's 22 degrees away, and say, what does Eve see before she gets the MetaSurface? Is she just lucky and gets a side lobe and all this worked anyway, and who cares about the MetaSurface in the middle? Or did she really need the MetaSurface in the middle to do her attack? So, so here you're seeing the frequency. Eve's target design is center frequency at 150, and she's targeting a wideband transmission, say 100 to 200 gigahertz. And so what you can see is she's receiving right at her own noise floor. So she's not receiving, she doesn't even know that Alice exists at this point. She can't receive anything. So there's not a significant enough side lobe in this particular transmission for Eve to be any threat at all at 22 degrees away from Bob. Now, Eve puts the MetaSurface in the middle between the Alice and Bob link, and then does her measurement. So with the MetaSurface in the middle, you can see the new blue line, and you can see that she's got somewhere between 20 and a 40 dB gain over the entire 100 to 200 gigahertz of bandwidth. So Eve's got a tremendous boost now. She can receive the signal. She's able to receive everything that Alice and Bob are receiving with sufficient gain that she's able to, for her receiver in this setup. Now, how about at Bob? So now we can ask the question about Bob, that if the MetaSurface in the middle completely destroys Alice and Bob's link, then they'll just re-steer away. They'll just view it as a blockage, right? I showed earlier in the talk, what if there's a blockage? They'll find a reflected path, they'll use the reflected path. Or what if there's a footprint? What if there's a resonance in these things? It's called a split ring resonator, right? What if it just completely collapses a frequency somewhere, and then there's a footprint for Alice and Bob to say, oh, look at this. This is clearly a MetaSurface in the middle. I'm under attack, and I'll discover it. All right, so this is without the MetaSurface in the middle. This is what Bob gets, and you can see Bob's getting a nice wideband transmission. at about minus 50 dB. And then with the MetaSurface in the middle, Eve attenuates Bob's link by about a few dB. So the interesting thing here is what it doesn't have. There is no sharp dip. There's no, the red doesn't sharply dip down at any particular frequency. And the gaps between these are on the order, it depends which frequency, it gets higher over here, but on the order of several dB. So hard to distinguish between relatively small scale mobility. So if even in our backhaul point-to-point links, there's some vibrations due to wind, buildings sway, there's a few dB variation happening. So this would be extremely difficult to detect. So the security takeaway is that the high frequencies and the high directivity give us both new security capabilities, meaning we can go super narrow beams, but also new threats as well, that we can have MetaSurface in the middle attacks that make seemingly highly directive transmissions vulnerable to diffraction attacks. So we demonstrated the MetaSurface in the middle attack above 100 gigahertz. There are some research questions, open ones. So I showed you our early results. We didn't have a programmable MetaSurface in the middle. We got rapid prototyping and we had less than $1, but Eve has to choose her theta and she's stuck with it. So if Alice and Bob, she knows where they are, then she can position herself to the theta of the MetaSurface she made. But if she'd like a stronger attack, then she wants a programmable MetaSurface in the middle, which we haven't done yet. Counter mechanism. So security, the question is, what now if we know, if Alice and Bob know that there could be an Eve out there, what are they going to do about it? And so some counter mechanisms. Well, what about sensing at Alice? Right? I showed you sensing at Bob. We don't have the THz radar in our lab, but you can imagine the radar that I showed might be able to get a reflection off of that, right? Because they are metal rings. So maybe Alice can actually use radar to try to detect whether the MetaSurface is in the middle. We haven't done that experiment yet. Or security-aware training. What if those rainbows? Remember, I showed you from Maxwell's equations what's happening as you go across. Well, the MetaSurface in the middle is changing things. It's manipulating those waves. So perhaps they can tell if they do a more fine-grained analysis of phase, right? Because when we did the beam alignment, we said, I don't even care about phase. Who cares, right? All we want to know is the gain of different frequencies. But if you're under attack, then phase could be the key to discovering Alice. And likewise, once Alice and Bob now try to do smarter stuff, then of course Eve does smarter stuff too, and the arms race continues. So a really open, interesting issue about how Alice and Bob can secure themselves at higher frequencies. Okay, so broadly, open challenges above 100 gigahertz. How do we create low-cost, energy-efficient transmit and receive components? Our circuits friends that I mentioned earlier are working hard on how to make the devices meet the constraints that we need for mobile devices. An open challenge, I think, for sensing at these higher frequencies. A lot of times at lower frequencies, the sensing problem is viewed as so complex because of the rich scattering that we use more black box style machine learning to try to understand what's going on in a room. So lots of training from prior examples. Here, the starting point should really be Maxwell's equations, that everything is behaving extremely well. But in the radar I showed you, there was no learning, there was no model other than Maxwell's equations. So it's just a very direct measurement. Yet, if you want to measure and understand more complex things about the environment, machine learning could be really helpful. So fusing the physics with learning, I think, could be really valuable going above 100 gigahertz. Diverse spectrum, I said 100 gigahertz and above was the beach, but that doesn't mean we don't want the lower frequencies. So they will be with us forever. You want to go through a wall, you don't want 100 gigahertz. You want to be sub 6. And so fusing those different frequencies in smart ways, I think, will be really important moving forward. Network optimization and management to harness these vast new features. One of the things that I think is really challenging is as we get these extremely sophisticated features at physical layer, they all have to be set up. And so what is that setup procedure going to be? How do we make it efficient? How do we make it secure? That's often the last thing to think about because we're so excited about how fast the data rate is that we don't think about that control plane side and the network management side. And then, of course, lastly, new security threats and capabilities. So to summarize, hopefully I convinced you that we should be thinking about above 100 gigahertz and all the way up to terahertz, that we get these wide bandwidths. So Shannon's happy. We get highly directive links through high gains. It doesn't have to be a phased array. It doesn't have to be a large number of antennas. It can be simple devices like leaky wave antennas. And these give us new sensing capabilities, ways of sensing that are just not what we've been doing in this community for the last decade plus. One-shot direction finding, so nanosecond scale way for all the receivers in range to know where they are related to the transmitter. And then the security, the Alice Bob Eve threat as well. So lastly, I'd like to acknowledge the PhD students and alumni in my group. These papers were all done by, that I've mentioned were from my group, were all done by PhD students there. So you can find more about the papers and the group members there. And eight of my students are here today, so they'll be very happy to tell you more about their work. Collaborators, Dan Middleman at Brown University, I mentioned him a couple times with the radar Rainbow, and also Josep Jornet at Northeastern University. The three of us have a terahertz scale project. And our sponsors, Army Research Lab, NSF, and then two industry sponsors, Cisco and Intel, who I thank as well. And with that, I thank you all for your attention.